Before I start today's class, I want to spend a couple of minutes just referring to the assignment number 3. So assignment number 3 about beam checking, I marked this one. I upload my markup back to you guys. Please don't ignore my markups, okay? Just go through one more very quickly, go through and see where I get right, where I got it wrong. And if you ignore it, simply there is no point of your submitting your assignment, because assignment is all about feedback. That's it. One thing I want to say before I keep going is most of you do not read lecture notes. Most of you. So I know someone, and I warned you last class. I said, before you start solving the assignment, you need to study. Study, it means read the lecture notes. It's very obvious, because simply the answer for question number 3, it comes straight from the lecture notes. And I can tell you, very few answer it the way I like, the way I listed on my slides. So again, not really super science. You just have to read the lecture notes. And okay, so that's one thing. The other thing is for the question 1 and question 2, it's about beam checking. And something like, for example, if you guys go back to the assignment, you will see I need to know where is the centroid. Where is the centroid? So when I say where is the centroid, you have to think for only few seconds, which is very simple. Number 1, do I have one layer of rebar? Great. If it's one layer are of the same diameter, so the centroid is in the middle of the rebar. What if I have more than one layer? So if I have more than one layer, it looks like the centroid somewhere. It depends on the symmetry. So if I have 2 layers of rebar and it is symmetric, it means I have the same number of bars and the same bar diameter. It means, here we go, my centroid is in the middle between the 2 layers of rebar. Anything else which is not symmetric or asymmetric, it means no, I have to find a way to find the centroid, which is you work like strength of material of first year, trying to find where is centroid. So I have kind of students who really are not paying attention. So number 1, what they do is say, okay, you know what, here is my centroid, it's in the middle. It's in the middle. So if it's in the middle, how come while the first problem, it has 3 bars on the first layer and 2 bars on the second layer, which means it's not symmetric. It means you have to put some effort. And the opposite is on question number 2, where I have 2 layers of rebar and it's 425 m on each layer, which be obvious, this is symmetric. Some people, they waste some time and they use the strength of material rule, like sigma A times Y divided by sigma A to find the centroid. So if it's symmetric, please don't waste your time, because simply you don't have to. Yes, you'll get the same answer, but you have wasted at least 5 minutes to come up with this number. It's as simple as it's in the middle. And guys, those are the things that you will complain in the exam. So in the exam, if you're not paying attention, you may feel that the exam will take way more than it should be. And it's not my fault, it's your fault that you're not focusing, okay? Anyway, so guys, please look at that. Please don't ignore my markup. Look it back, because it's going to help you in your midterm exam, which is on Thursday. One last thing before I start, you will see I'm going to send you an email tonight. So I'm putting a deadline for myself tonight about more information about the midterm exam. Like, for example, where is the cutoff point? How I need to get prepared for the midterm exam. During the exam, what should I do? So please, this email, please read it by heart. Read this email by heart. I will do my best to be thorough, to give you a full picture of what's going to happen on Thursday. And I'm gonna write it on the email, but I'm gonna say it explicitly now. Guys, rules of the exam they are still applicable, whether you do it online or in class. Cheating in the exam, it's a fatal mistake. And you know, I don't want any one of my students to fall into this trap. But if you fall, please don't blame anyone. Just blame yourself. Don't think that you're covered, that you know, I'm in my room. There is no one can simply catch me. If you're caught, because remember, you know, we are in online time. If you're caught, I will insist that you will be outside the program. We don't want any cheaters among us. Our reputation is so high. Our graduates have good reputation. I don't want to put another one who doesn't deserve in our group. As simple as that. Okay? I'm not threatening you. That's for you. If you really feel what I say as a professional member of our group, then please, all you want to do is just study and write what you know, not what others know. We have cases already, and those cases you will see it will not be let go. You will have to be punished, or you will be punished whoever decided to cheat. Okay? It's very simple. We don't want to have a bad people among us. Simple as that. Anyway, I'm done. That's where I'm going to start right away. Okay, guys. So, guys, look at my screen. I have to probably start recording. Actually, I did. So, guys, I already passed this point, and I know, and I just make it a little bit pretty. I went back to my slide. There was some missing information, or maybe I said it in verbal, but I want to be documented in writing. So you see here a graph, very, very nice graph. This graph, it kind of summarizes the entire process, although it's very simple. So on this graph, I'm showing the reinforcement ratio. The reinforcement ratio for sure, it cannot be negative. So it cannot be less than 0 for sure, because we have to add some rebar. We start from here, from this point here, where we say, you know what, reinforcement ratio is equal to 0. What does it mean? It means I have plain concrete beam, a beam that has no reinforcement. Now we know that if I do that, my beam will be very brittle, will fail, sorry, in a brittle way, because concrete will fail in tension, and it's brittle as well, and it will fail at a very, very early level of load. And that's why we must add some reinforcement, as you know. And then we add some reinforcement, and even this zone here in red, it's also forbidden, because even you have some little reinforcement, it doesn't ensure the ductility of your failure. Still, your beam will fail in a brittle way in tension. Then the code will give you here a minimum. You can see this is the value from the code, where it gives you a minimum reinforcement that you should include in your beam. We cannot add less than the minimum. So I said here the solution here, what happens if my area of steel is small in this area? All you have to do is just push your area of steel to be equal to the AS minimum as defined by this equation over there. Anywhere between this point here and this point here, this is your work zone. This is okay. Continue. No need to change anything. However, if you found out that you are in this zone, it means your rho is more. You can see on the gram, if your rho is more than this number called rho balanced, which is F prime C divided by 1100, then stop. You can see I made it bold and it's red. Stop. Don't continue. It's a compression failure. It's a brittle failure. It's overly reinforced beam. And here is the solution. So the solution can be one or combination of those. I color in yellow, I said increase beam or height or width and FC dash. And those are sometimes visible and sometimes not visible. You have to check with architect, or maybe you need to make sure that your concrete is not super strong. Okay, like more than 40 MPa. And the other option, which will always be visible, that's why I color it in green, it is compression rebar. Okay? Anyway, so again, this is a very nice summary and puts everything in one perspective. Then, guys, what happened next is, after we finish, if you guys remember, this what we've done the last class, we simply found what's the area of steel. We turn it into number of bars and bar diameter. We make sure that it doesn't exceed the rho balanced. And on the meantime, we have area of steel more than AS minimum. Guys, with this, guess what? You finish only one phase of the design called ultimate limit state. How about the other state called serviceability? So serviceability is here, and we talked about it on brief. And we said in Tahir's class, we will only do crack check, cracking check. We will not to make sure that my cracks are not so wide, because if they are so wide, you know what happens, huh? So anyway, when we look at crack checking, what we do is we look at the bottom part of the beam, half of the beam under neutral axis. Why? Because this part here, it has tension and concrete cracks in tension. How about the top that's above neutral axis? It is compression. Compression tends to close the crack, not make it wider. And in this context, what we do is we split this area into two zones. The two zones are colored in different colors here, so you guys visually have to look at those zones. A zone number one that is surrounding the main flexure bars, okay, in green. And the zone number two, they are on the side of your beam. Okay, how do we do that? Zone number one, it's all the time. So all the time, we need to check zone number one. Make sure that the crack width is acceptable. How about zone number two? Zone number two is only when the beam height exceeds 750 millimeter, and that's from the code. Okay, now, for zone number one, quickly, we estimate this number here called Z, which is crack control factor, from this equation here. Really, what I want to remind you is the difference between Y, DC. So you can see here, DC is always the distance from the bottom layer of rebar. If we have one layer, great. On the right side here, we have one layer. So the centroid is exactly from where I measure DC to the bottom of my beam. But, or however, if my beam has more than one layer, so the DC will be different from the centroid. So please, you probably need to focus much on this one. So on this picture here, where is D sub C is from the last layer of rebar to the extreme fibers in tension. How about the A? So the A is simply the area of shaded area. And how you do this one? Number one, you find centroid. So the centroid is marked by distance called D prime. You take the D prime and you mirror it. So you take D prime, multiply it by 2. You can see in the equation, it is 2D prime multiplied by the width of your beam. And this will give you the green area, And then finally, you need to, don't forget to divide by the number of bars in this one. In this picture here, we have 5 bars, so we divide by 5. In this picture here, we have 3 bars, so we divide by 3. So this number here is the number of bars in this green area. Now, next is once you're able to find your DC and A, and remember always the Z is equal to 60% of F yield. I'm sorry, the FS. So you can see, I'm sorry, this part here. The FS is always 60% of F yield. Once you're able to do all the calculations, you find the Z. So in our problem, the Z is equal 19,598. If you want to make sure that your beam is acceptable in terms of cracking, very, very simple. All you have to do is you compare this number against a limit, a threshold. This threshold, it depends. If the beam is exterior beam, so my number or the limit will be 25,000. Anywhere below 25,000, you're okay. It means your crack width is not big enough or acceptable. If your beam is interior beam is protected, it's not exposed, then the difference is this number is not 25,000 anymore. It is at 30,000. And that's why we allow more cracking for interior beam, because interior beam are protected and we can go for a higher number for the limit. Okay. Now, any questions so far? Any questions so far? No? Great. Let's move on. So guys, next is skin reinforcement. What is skin reinforcement? It's this, it's there in this picture we call those bars in cyan, those 4 bars, we call them skin reinforcement. Are they always required? Do we have to provide skin reinforcement all the time? No, it is only when the overall thickness of my beam, which is H, is more than 750, which means 800, 850, 900, and so on. In this case, we have to provide what we call skin reinforcement. You can see it's very obvious. It's very clear. It says here exceeding, if H exceeding 750. So what happens, I'm going to show you again. This is kind of hard to read, so I'll kind of maybe I will switch back to it whenever required, but really this is what you have to do. So what we do here is, guys, is simply we need to figure the area in magenta, or the shaded area. So how can I find the shaded area? Very simple geometric problem. Remember, this line here, it marks, this line here marks half of your beam, which, as you can see, I label it H/2. So if your beam is 800, this dimension is 400. And we already, in our check number 1, for zone number 1, we figure out D prime, and then we mirror it, so 2D prime, which means my Y is very simple. It's going to be H/2, 400, for example, or in our example is how much? Is 900/2. So 450 minus my D prime, which is 55. So which means the distance, this distance Y, is very simple. It's 450 minus 2 times 55 millimeter. So you'll get the Y is equal to 340. How about the X? So what you have to do for the X, you have to find the distance from the outside of your beam to the centroid of your skin reinforcement, which is not super science. It is the cover plus stirrup plus half skin reinforcement bar, which is always 15 m. 15 m. Once you find this distance, you multiply it by 2, then you get the X. Why 2? Because we mirror around the centroid of reinforcement bar. Okay, so I guess, guys, this was 47. If I remember correctly, this was 47.5, and if you multiply 47.5 times 2, so which means X equal to 95. So great, we know the X, we know the Y, so we multiply X times Y. Why? Because it's a rectangle. The shape of this shaded area is a rectangle. So 340 times 95. So the area of this guy here, the area of this shaded area is 32,300 millimeters square of concrete. Now, how do we find how much steel do we need? We simply have to figure out what is my skin reinforcement ratio. Remember, we always use in this class rho, and rho is reinforcement ratio. If I add here subscript SK, it means reinforcement ratio for the skin rebar. Okay, where did I get this number? From the code. Go back to the code, and the code says whenever your beam is exterior, then we use 0.1%. Okay, whenever my beam is interior, so the raw skin is 0.008. Very simple. You decide where is your beam. If your beam is protected, we need to worry less. So we add only 0.8%. If my beam is exterior, so I need to worry more and add more rebar, so I add 1%. Now, so after finding area of concrete and then multiply area of concrete times the skin reinforcement ratio, I get here, finally, I get the area of steel required. So you can see it's a 323 millimeter square of rebar. And this will turn into 215 m each side, because a 15 m each is a 200 millimeter square of steel. So which means 215 m is 400, which is more than 323. It means we're okay. Now the last check is the spacing. Why is that? Because look at this. The code has also some constraint. Please read. So the maximum spacing between skin reinforcement shall be 200 millimeters. Okay, so I need to make sure that when I add 15 m, 215 m, this spacing here, I'm going to mark it for you guys. The spacing here between this point and this point here, this should not exceed 200 mil. So you can see on my slide, I said the spacing between the skin reinforcement is 340 over 2. So this number is 340 over 2, which is equal to 170 mils. Okay, why is that? Because simply we leave from this bar to the end of zone number 1, we leave a spacing over 2, and from this bar to the middle of the beam, S over 2. And because of that, so how many spacing I do have? I have 2 spacing. One more time, guys, one more time. So one more time, from this bar to the end of zone number 1, I will leave half spacing. This is S over 2, okay? And then also from this bar to the top, how much is that? So this one is also S over 2. So you can see I have S over 2 and S over 2. So that's 1S plus 1S. So we have 2S. And if I have 2S equal to 340, which is Y, then my spacing between the skin reinforcement is 170, less than 200. So that's great. The last statement, which I said it on a very, very quick basis. Very quick basis last time. I said skin reinforcement can be used for estimating flexure capacity. And by the way, that's in the code. Please read. Such skin reinforcement, that's here, such skin reinforcement may be, look at the name, may be included in the strength calculation. So if you want to include it to take some moment, of course, code allows you to do that. However, I can tell you myself, I myself, as a designer, will not really include it in my design. And that's, by the way, that's kind of a general thing. I do it all the time. Guys, look at this. There are 2 situations. One is design. The other one is a check. Check it means you have existing situation. So the beam is already built. And what is my job is to say the beam can survive or it cannot survive under the new loading. You know what? If the problem is a check, I will justify and I will use my skin reinforcement to add extra capacity to my beam, because the reality is it will do that. However, in my design, I'm not going to bother. I am going to let it work on and deal with the shrinkage on the side, and I will add enough reinforcement at the bottom. Okay, hopefully you get the idea. In a check, I will use everything possible. And the code says you may. It means I'm allowed. It means I can use it. So I will use it to make sure that my beam will meet the requirement and safe. Okay. In my design, because design, nothing is built already. Nothing is built. Everything is in my hand. No, what I will do is I will not use skin reinforcement to help with the main reinforcement. I will just put enough rebar to deal with the bending moment, and then I will let skin reinforcement to resist the shrinkage by itself. Hopefully this is clear. Are you guys following? Thank you so much. I like what you're doing right now because it gives me the sense of where I'm going. And thank you for turning on your cam. Okay, now. So guys, here is some detailing. So I want to show you what do we do after we spend lots of numbers and thousands of calculations. Not 1,000, not 3,000. It just takes some time because I give you all the details. But we've done a significant number of calculations to design our beam. And here is my final finding. My final finding is my beam needs to have a 530M. I need to add skin reinforcement 225M. Sorry, 215M each side. Have to place here some rebar in green called stirrup hangers, which minimum 220M, because every corner must get a rebar. So you cannot add one. You must have one on each corner, 220M. And then later on in my course, I'm going to show you how to design the stirrup. But for now, I set 10M stirrup at and then dash. Because in my course, you will learn how to find the spacing between the stirrup. But for now, let's leave it blank, dashed. Also, I showed my height, 900 mils, and then the width is 450. What do we call this? It's a beam section, huh? And that's what you will summarize all your finding. Because remember, you think somebody is patient to look at your numbers on site? Nobody cares. It's your business. It is not of our business. Just give us something to build off. And that's where I have to show some cross sections. Now, just for fun, guys, this floor level here, probably by now you miss it, huh? I myself miss it so much. Probably I'm gonna cry now. So this is the structural plan view of the 4th floor of Aldrich Center, where I used to live for 6 years. My office. So you guys remember, huh? This is the elevator here. You go outside from the elevator, then you turn left, and then this is the stairs, which we always take when this is broken, and it's broken all the time. So we turn left, and then we go here. Remember, huh? This is my way every day. I go here through the doors because this is the reception. And then if you met any of the instructor last year, probably they met you in these rooms. Huh? There are some study rooms here. I just wanted to show you some plan view of something you know and probably you miss. Why I'm doing this? Because simply, please focus. In a plan view, we do not show. We only show something called beam mark. So where is the beam mark? It's over there. Okay. I call it CCB 4-35 because this is on the 4th floor. You can see where is the number 4 coming from. So that's 4th floor, and it's a beam with mark 35. Do you see any reinforcement here? You don't see any reinforcement. So it tells you if you want to know how many bars or like that. So all you have to take from this plan view is the beam mark CCB 4-35. Then how far all this business, where can I find? Let's go to the next slide. So on the next slide, again, this is kind of a little bit of something called beam schedule. So for Aldrich Center, the beam schedule is so big, it comes into structural drawing. I just take a little bit of it so you guys get the idea. So where is CCB 4-35? I'm gonna box it for you. So it's over there. Huh? So this is beam CCB 4-35. And I'm gonna give you guys some time. Okay, I'll give you some time to understand what is in this schedule. So number 1 is the name. What else? Can you please go through individual columns and see what is available in this row? Start off from 2nd column. And again, not very difficult, just have to read the header. Huh? So the header of the column is beam size, W times D. It means what is the width of this CCB 4-35? It is, I'm going to zoom in, it is 675 times 950. That's the width of the beam times the height. Okay, now, what else? What else? Guys,
the support.
can you please? Okay. Yes, true. So, guys, it's not very clear, and probably I need to shade this one here. So, if I draw a box here, so this is the support, huh? And probably we can give it a hatch, like this hatch here. So this is a column, okay? And also on this side here, that is my right support. So there is a column here as well. So there's another column here, okay? Let's give it a hatch. Okay, so what happens here, you can see, so the beam is 675 by 950 depth. Here is the reinforcement. So it's the reinforcement is we have a 430M going all the way between the columns. Between the columns, I have 4 continuous 30M. And also somewhere in the middle, I have another 430M. But those guys, you can see from the picture, they don't go all the way to the support. Does anybody in this class? So, which means for this beam, I have some location, I have a 30M, and then in other location I have 430M at the bottom. Does anybody in this class can tell me why do that? Like you can see from the picture, there are 4 bars, 30M. They extend all the way from column to column, while there are some additional 40M. They don't keep going all the way to the support, rather than stopping somewhere here and somewhere here. Does it make sense for you?
Would it be because of a greater bending moment in the middle?
I'll give you, would you be happy if I give you 5 marks for that?
I'll take it.
Okay, thank you so much. So Martin was so fast, and he said, you know what? This does make sense for you. Thank you, Jelly. You will be next. I know that you have lots of mark here. Okay. So guys, Martin was correct. He kind of noticed that the shape of the bending moment. So the continuous beam in the middle, there is a maximum positive bending moment. So because the bending moment is so big, so I need so much rebar. However, as you go close to the support, what happens to the positive bending moment? Remember, in a continuous beam, we have positive and negative. Okay, so I'm talking about now the positive. As we come close to the column, what happened to the positive bending moment is it decreases. So since the moment decreases, so then I need less area of steel, and that's where I stop. So this does some saving. So this one saves some. Let's go back now. So also you can see on the same diagram, there is something called 15M, 315M, HEF, 315M, HEF. And by the way, I'm not asking you to know what is HEF because it's not secret. If I print for you the first few pages of any structural set, they have the abbreviation. So please don't scratch your head and say, okay, what is HEF? Simply you go to the notes page, and on the notes page, it will tell you HEF is horizontal each face. Horizontal each face. Okay? Horizontal each face. And can you guess who are those or what are those? Hello? Anybody can guess what are those? So the 430M and 8M, those are for flexion, for bending, for bending. Okay? What are the 315M horizontal each face? Show your hands, please.
Skin protection.
Who said that?
Dominic.
Okay, Dominic, you will get 3 marks for that. Okay, so yeah, true. True, guys. The 3, and you can see each face. Look at the name, each face. It means exactly same as we finished a few minutes ago. We add 315M. I'm asking you here, why do you need to add here skin reinforcement? Because of this, Watch this, please. Do you see this 950? 950
Yes.
is more than 750. It means must add skin reinforcement. How about this guy here, which is only 650? What do you think? Do we have any skin reinforcement?
No.
Don't.
No, because of the depth. Because of the depth. So anytime, and you can see another beam here, which is 37, we have a 950 and we have a 315M each face. Now, as we are looking at this picture here, so that you can see there are some rebar are going on top of the column. Let's go back to, I'm gonna clean because we have to focus for our beam, which is beam 35, I guess.
Yeah,
So
35.
beam 35, obviously beam 35, look at the right support. Do you see what happens to the top bars? They are bending down because this beam is not continuous. It stops and it doesn't have any right span. However, on the left side here, look at the rebar in blue. Look at the rebar in blue. So my rebar is in blue and going on top of the column and keep going to the next span. Let's check this on the plan view. So on the plan view, what happens to the right of my 35? There is elevator. So my beam, you can see here is my beam. It doesn't continue to the right. So that's the last span on this side. However, on this side, on the left side, we have a beam called 34. Now, if you want, what are the reinforcement of 34? Very simple. You go down here and look at beam 34, which is here, and you can see Okay, you can see here is 34, which is the same. Actually, they changed the depth of the beam, so they went from 950 to 650, and again, it is only one span. So this is beam. I'm gonna probably box it out. So this beam here is beam 34, and so where is beam 35? It is to the right here. Okay, that is how we read. By the way, so you know, schedules are more super handy and very important. Schedules, and please take this note, schedules are super important. Why? Because simply it prevents confusion, it prevents mistakes, and I will share with you why. I didn't feel it before I did my actual design myself. Okay, guys, if we simply put our reinforcement here on the plan view, okay, that's not a good idea. And simply the only place in the entire set where it's talking about the reinforcement is here. The only place in the entire set where it explicitly mentioned how many rebars is here. So guys, what happened is, this is for the changes. If anything changes and the designer went back and changed the numbers and came up with different reinforcement, so there is only one place in the entire set that he or she need to change. Otherwise, if you don't have a schedule, it will be messy, because simply you have to trace where is the reinforcement everywhere in the drawing, and you have to change it. Otherwise, it will be super confusing if the contractor look at the drawing and somewhere it says 420M and somewhere else it says 425M, you will get phone calls and crazy. So schedules are important, very handy. With them, we can avoid mistakes and confusion. And by the way, schedules you will see in any structural set, you will see beam schedule, you will see column schedule, footing schedule, everything comes in a schedule. Whenever you do change, you only change the schedule, but don't have to change or trace the change in the entire drawing. Now you can see here, we also talk here about the size of the stirrup. So it's 10M, and this is how the stirrup will look like, as you will learn in my class in a month, probably 3 weeks from now or 2 weeks from now. Okay, and then the spacing between the stirrup is 350 millimeter on center. Okay. Now this thing you will learn in my class shortly, and this thing you will learn in my class shortly, and this thing you will learn in my class shortly. But this is about the shear, huh? It's not about bending moment. Okay, Domenico? Stirrups, they don't do anything for bending or flexure design. Okay. Now, again, I don't have time to go through those, but I just cut them or got them from the structural set of Aldrich Center, and those are sections through the beam. You can see here in the beam, somewhere on the plan view, it says here there is a section, and this section is section 6 over S 50.11, and this section here is section 3 over S 50.11. Guys, very important, because some will wonder what is the section look like here. So simply you have to go to the drawing S 50.11. Then what you do is you look for section number 6. So this 6 is the section number. This 6 is the section number, and at the bottom here, that's the drawing number, and that's the reference. Very important, huh? So if you want to understand how the section look like, you just go to this drawing and look at this section. Now, again, probably you've seen it already. I'm not sure if you guys crazy like me. When you go around, you look all the time up and see how things are connected. I myself do that all the time. You guys remember section 3, it shows you where or how the metal deck is connected to the beam. So here is the beam, which is a beam 34 on the 4th level. And if you guys remember, in the Aldrich Center, it is simply concrete topping on top of a metal deck. And there are some joists, steel joists, connected to your beam. Also, if you guys remember, at the bottom, there is a big truss. So, and there is a kind of a bracket plate connected to the beam. Anyway, if you cannot remember, no big deal for me. Again, those are extra for fun if you are interested. Okay, now, any questions so far? Let's see. Let's see. Guys, any questions so far?
Not for me.
Not for you. Martin.
I'm just wondering, is it always, you kind of mentioned this, is it always 15 bars for skin reinforcement?
Yes, it is. Let me check, because as an engineer, I will never use anything like less than 15. But let me tell you, let me check the code, because really the code is the bottom line. So the code, when it comes to the code here, quickly, I don't see anywhere where it says 15M. I don't see anywhere. So the code is talking about about the spacing, about the area, raw skin, but there is no mention of the 15M. But I can tell you, I have designed so many beams. I never use less than 15M. I will never use less than 15M. But that's not the code. That is the best practice. Okay, thank you so much for that. Any guys, any questions so far? Jelly, go ahead.
Yeah, but why can't you use 10M, which is I think much better to than 15M, depending on the area you found, the total
Uh,
area.
well, I cannot say no, because the codes never said you must use 15M. So I cannot argue with you, and and enforce my Tahir's rule to you, because it's the code. The code has only one limit on the area and another limit on the spacing. If you meet those two limits, then I cannot say no. But I'm telling you, Tahir, engineer, uses all the time 15M.
Okay.
Okay, guys, any other question? I want to hear some noise, because we're starting a new problem. Okay, guys, you can see things went very slow, and it's not really slow, because so we've been working on one problem now for more than 3 hours, from the start of last class until now, because I go into a very small details. However, don't never expect that when you solve one problem, it's going to take you 3 hours. That's only because I go into little details. Okay, and that's, by the way, from this point on, I'm going to speed up, because you're supposed to know the rule. So all I have to do is give you a reference to, for example, skin reinforcement, like area of steel, all those things. I'll just give you a quick reference to it. Okay. Now let's move on. We still have 10 minutes to the break, so we have time to go and give you at least the start of the new problem. So here we go. Here is my new problem. And you have to understand that the problem that I give you, which is total of 4. So in my class here, you have 4 solved example. 4 solved example. Number 1, and it's very important to understand that, Number 1, I never ever say it's simple beam, or I never say anything. Okay. I'll go back to the header of my first problem. All I said at that time is here, Here we go. Here is the header. Actually, I never said it's a simple beam or anything like that. All I said is, here is some information, and here is the moment that you're supposed to resist. Here is some information. Here is the moment that you're supposed to resist. I gave you the moment. But let me ask you this question. Do you think this is a realistic problem? Like when you graduate and let's say you work for a structural design firm, somebody will say, okay, Mahdi, take this number and design your beam for this number. Or somebody will give you a plan view where you will find the 800 by yourself on your own. Which one you think will be more realistic? Guys, you're so quiet. Gord, what do you think?
I would think you would get a plan view, and then you kind of got to find your information yourself.
That is correct. 100% correct. You are correct. So in real life, you should start from scratch, from ground zero, where you will find all the loads and all the bending moment, and then you could go from there. However, if I do that, trust me, you will never love my class. You will never follow, because you will be distracted by other side information. So what happens here, if you guys go back to my slides, As soon as I'm able to derive this equation, I want you guys to apply it right away. And so that's what I did. I gave you the moment, and you can see immediately once I give you the moment, you're able to find area of steel. However, as I said, this is not very practical. In real life, you will probably have to find the loads and the bending moment on your own. So that's why I give all the examples in kind of a graduation. It is gradually I design my lecture and my example. So to gradually, to at the very end, you will do that. So to give you some comfort and trust, here is what you will do at the very end of my lecture or series of lecture. Okay, here is the very end. So you can see my last example, number 4. Number 4 is there is no moment given to you. It is what is given to you is a floor plan. So you have dimensions, you have thickness of the slab, and from there you will do everything until you design your beam. But to be honest, from teacher perspective, I cannot do that right away. I have to take you gradually to learn and learn and learn, and this will be my final example in this class. Okay. And by the way, so you know, assignment number 4 will be, I would say, copy. I'm not saying I'm based, it's copy with some modification of example number 4. Copy and some modification on example number 4, but you have a solved example of number 4 in details here, and that's what you will have to do that in assignment number 4. Assignment number 4 is, I did it, but, and let me look at the MS Teams, and probably I need to look at your face. It's already finished. It's already finished, but to consider your emotion and your stress, I didn't publish it. Okay, I'll publish it after the midterm exam. Okay.
Thank you.
No problem. Okay, so and you'll get, I mean, you will get enough time to solve it, so don't worry about it. But I just I work ahead because we don't know what's going to happen tomorrow, so I kind of work proactively and prepared assignment number 4 for you. Okay. Again, no super science. It will be a copy with some modification of the example on my notes. And that's why please, 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 please read the lecture notes. I put a lot of effort to do that, to make it the way it looks like right now. And it's not easy. Probably one slide can take, sometimes one slide can take 1 hour because I need to make a Revit model and make you a good material. Okay. With this being said, I probably will break. Okay, so guys, we'll take a break. We'll come back here at 1:58. Thank you.